And when we look at artificial intelligence, we first have to ask the question, what is actually intelligence, right? And there, the discussion already becomes quite interesting, because when you look at what a brain or a neurochirurg thinks about intelligence, it's completely different from what a psychologist thinks about intelligence. And then you have all those fancy tests online to test how intelligent you are, and they're all based on a construct where at a certain point of time we defined, I think this means to be intelligent, right? And then came artificial intelligence. And artificial intelligence is a nice buzzword. I think most people that work in the field can agree that we're not there yet, right? We have come very far in machine learning, but we're definitely not at a point that we're actually artificial intelligent. But to work with a certain definition, I take one that is actually already quite old, right? And it basically says artificial intelligence is the field of study that gives computers the ability to learn without being explicitly programmed, right? So for the ones that don't program, right, normally when you write code, you actually say, if this happens, then do that, or do this, else, etc. So you're really explicit in what the thing has to do. The goal with artificial intelligence, or at least in a computer science area, is to not say those things at all. You basically want the computer to learn by itself so that next time when it has to do something, it does it correctly, right? And this sounds quite easy. As you see, 1959. So it's not that we started thinking about this the last few years. When you look at the core algorithms, the core mathematical models behind all of this, I think most of it is actually developed in the 70s and 80s, right? The first computers, the first ideas about what would be possible in the future. And we still rely a lot on these mathematics. So what has changed, right? And I think the main thing that has changed are two things, actually. One, cheap computing power. For the ones that are a little bit older already, I'm not sure if you remember buying your first PC or working in a company where you're allowed to work with a mainframe. An hour of a mainframe would cost you a small car, right? The first PCs that you had to buy, those were really, really expensive. And they had the computing power of not even 1% of what you currently have on your mobile phone, right? So when you look at how that developed the last few years, or well, let's say the last 20 years, actually going past Moore's law. Moore's law is every 2 years the capacity doubles, right? We're way ahead. And this allows for all the mathematics that were developed in the 70s to actually run in a period of time that we don't die in between, right? Because the first algorithms, when you would actually run them on a PC, you had to wait 40 years before they were done. So the second thing that has changed is the availability of data, right? In the 90s, 2000, etc., companies started implementing central databases. Then we got the internet, people started publishing things, right? But the amount of data that has been collected in the last 10 years, it's crazy, right? You can Google it a little bit online. It is really, really crazy how much data is accelerated, or the collection of data is accelerated. So why? It actually comes back to the first point, cheap hardware, because suddenly the storage of data is incredibly cheap as well. When you look at how much you paid for that 3.5-inch floppy disk and how much you now pay for your SD card, that's a big difference, right? So in general, you can say those are the two main things that have changed. What now came to it, and that basically made the acceleration of the last few years so fast, is cloud, right? Cloud is also a bullshit word, the same as artificial intelligence. Cloud just means it's somebody else's computer, right? But what really changed with cloud is the concept of SaaS, software as a service, right? And that means instead of programming stuff yourself or buying expensive programs that you only need for one day, you can actually access all that knowledge in the form of a service for almost free, right? And that means, and I think this is really one of the core pieces that you should take away today, AI is a commodity, right? There are only a few companies that really build their own AI that is worth building. Everybody else is just buying it off the shelf. You buy a few data scientists, you rent some AI capabilities at a cloud provider, and anybody in this room can start its own AI company tomorrow, right? AI is a commodity. When you look at AI and you want to group it a little bit, right? And you can use many different groupings. This one just works the best for my talk. Go online and you find different groupings. But in order to explain a little bit the differences in the concepts, I took this one. AI, it's wide. In my opinion, it does not exist. We're working on it, right? But we're not there yet that we really have artificial intelligence. What we have is lots of really cool machine learning capabilities, right? And when you want to split them up, one grouping is then supervised learning. Supervised learning means I take a big data set, I label that data, right? Then I run certain algorithms, and then based on what was learned, they can make a decision afterwards. We'll get to a few examples. Unsupervised learning means I have data, but no labels. So for example, when I have a lot of patient data, right, with lots of patient outcomes, I just try to group that group of patients in different clusters without labeling them up front. That's a typical unsupervised learning. Then we have reinforcement learning. That's how we actually learned as humans, right? You get born, your parents show you certain things. When you do well, you get a cookie. When you do not so well, well, in the old days you got a smack. Nowadays you get another cookie, right? But that's why the learning doesn't happen so fast anymore. So this is the typical reinforcement learning, right? So and then you have the deep learning. Deep learning is another nice buzzword, right? In the old days, it was just called a neural network. And a neural network is actually the most close to how our brains work, right? You have certain inputs, then you have a network in between, and then you have outputs. And you can train that network based on data, but you have no clue what happens inside. They typically give the best results, but because you don't understand what happens inside, they also limit the use, right? Because if something is generated by AI and you can't understand how a decision was made, you have very many legal obligations that you cannot fulfill. When you talk about audit trails, it's not possible anymore, right? Oh, I decided to not treat that patient and let him die. Why? Well, my AI said so. It's going to be interesting, right? So, and the whole generative AI is actually part of deep learning. Generative AI, the large language models, is nothing else as a bunch of neural networks switched together, right? And I know when we have a scientist in the middle, you can argue about a lot of things I said. I really tried to make it clear in a way that you still remember tomorrow. So, our challenge for today, we are going to do a little bit of a thinking experiment. We're actually going to build an AI company together, And the goal of the company is to build a classification for startups. We want to predict if a startup is going to be a good startup or not a good startup. So the goal is to replace ourselves, right? Because that's the story in the newspapers. We don't need humans anymore, we have AI. So let's try to do that today for ourselves. Then we don't need the Business Angels Club anymore. We have the Business Angels Club algorithm. Huh?
And we can then meet only for dinner.
Exactly. Don't we already do that? So, predicting a good startup to invest in. That is the goal, right? That is what we try to do. 2 words are actually quite interesting in this sentence, right? Good and startup. What is really easy to express as natural language, right? I can explain what I think a startup is not so easy to understand for a computer. So the first challenge we have is, how would we describe a startup in a way that is understandable for a computer, right? Anybody some ideas?
Crazy idea, crazy people, and family and friends.
So with crazy, it becomes already interesting how to define crazy, right? But some things, right? You could say, how many founders, right? You could say the average age of founders. Allegedly, that is actually quite a decent predictor for success or not, right? You could say how much was already invested. You could take burn rate. You could take revenue. Yes, well, usually that is 0, huh? So valuation.
Patents?
Patents, yes, no.
Market opportunity.
Market. Then at the same time, industry, right? So, there, competition, right? So there could be many infos that you could use to describe such a startup. And I made a very small example, which is a terrible example, but it gives you the idea. Right? In the end, you will create just a huge big table with each line representing a startup, and each column is a so-called feature. And one line is called a feature vector. The ones who paid attention at mathematics in school will understand where we go with a vector, right? So feature vectors are quite important when we talk about anything related to machine learning. And this is only a small one, right? So the first company I worked in, we actually worked on document classification, optical character recognition. To describe a single character in an OCR, we actually had 1,200 features in a single vector. So you can already guess that it takes quite some computing power to actually do something meaningful with such a vector, right? So I think everybody can come up with 100 other things. If they are relevant or not, we don't know up front, but important, in order to start doing something, you have to create a feature vector. Even with all that generative AI nowadays, your feature vector is just a sentence. The sentence with all the letters in it, and that is basically used. So the second cool word in the task is good. How would you describe a good startup?
Just one question. You should rank also these factors.
I can only rank if I understand what the relation is to good.
To success.
Exactly.
Whatever.
And then it becomes interesting, because my definition of success might not be your definition of success, right? When I sit,
Unicorn.
when, so then we can stop. We have not had a unicorn here yet, right? No, but it's
it corresponds to our criteria. Makes it good.
exactly. But yeah, so good is you want to have a good outcome, right? And a good outcome is typically, I would say, defined as an exit. And you could even say an exit with a certain multiple, or you could actually say, hey, I would really want to have that unicorn, etc. But I have to have a definition of good, because if I don't have a definition of good, I cannot train, right? That's like the childs nowadays, they just get cookies, so everything is good, right? So I have to have criteria to say what is good, what is bad, what is so-so, right? So when I have those two, then I can start thinking to the next step. And the next step is, where do I actually get that data? Right? I have defined my feature factor. I know exactly what I want to have, right? I also know what is good, so I know how to label them. But where do I get that data? I can take the BAS database. That is a little bit small to actually do some meaningful testing. I could try to buy data from Crunchbase. I could try to buy data from Delum. I could try to buy data from venture capitalists, right? But I need to have that data. And not just a little bit, I actually need a significant data set in order to train, right? The smaller my data set, especially in such a wide space, the less good my algorithm will be in the end, because I only train what I have seen before. Right? That also means, per definition, that I only train what happened in the past. Right? So if I don't include additional learning in existing models, my model will only be as good as the past reflect the present. Right?
Nico, sorry, one question. What's now the difference between the normal profiling and AI? Because if I have two of these feature factors, I have a two-dimensional grid where I could theoretically simply filter and then get to a result and say, this startup makes it good, this does not make it bad, but
So-
that's not AI. So what's now the difference to AI?
That depends on how you formulate it, right? Because what you describe is just a decision tree. And there are lots of people that sell decision trees as AI, because decision tree is a core component from machine learning. And yes, many just do that. We get to the decision tree afterwards, right? But with any startup that actually talks about AI, you have to discuss data. Where do you get the data from? Is it legal, right? So I wrote a few books, write lots of articles, and I have everything open online. So when I now use ChatGPT and I ask certain questions, I get my own shit back. It hurts, especially when it's older. Even I learned in between. But it's my shit, right? So when somebody else is actually making money with it, I don't like it, right? But that is what ChatGPT is. It collected data from the public domain. It just gets data from Wikipedia. We get to a lovely example afterwards, but I bring it now. Stack Overflow. Everybody in programming world knows it. It's the most popular forum for computer programming problems, right? Everybody that has a question puts it in there, and then you have an army of nerds that want to prove that they're the smartest, and they give the answer. And then they actually have a voting system, so the whole army actually makes sure that only the correct answer wins. And the quality is amazing, right? You don't have to study computer science, you just need Stack Overflow, right? And then ChatGPT came. And ChatGPT is when you ask a question with the same programming question, right? You actually got a huge answer, explaining the answer, writing the code for you, putting comments in the code, actually writing clean code. When you ask the question on Stack Overflow, you actually got an answer, hey, are you stupid? This and this is it, right? Make it happen. So what happened? Everybody used ChatGTP instead of Stack Overflow. I will show you a picture afterwards, but the traffic actually went down, right? So the problem is 50% of all those answers that ChatGTP gives is wrong because they didn't train on the correct answers, they trained on all the answers. And then you had those nerds that wanted to look smart that actually started posting the answers of ChatGTP on Stack Overflow and actually ruining the quality, right? So, and ChatGTP needs Stack Overflow to actually get good quality. So now we have a vicious circle that makes our AI dumber and dumber and dumber and dumber, right? So that's an interesting problem. So where do you get the data? Really, really important. So let's assume we bought some data from Delum, and we also have our own BAS data. And when you look at it, well, look at Delum. How many of you actually have all the rounds you invested in Delum, right? How up to date is your profile information? How up to date is the startup information? It's not, right? It's an absolute mess. So yes, I bought the data. It's still shitty. What do? I have to start cleaning it. Whoa, there we have a few interesting problems. First problem, let's say we have industry. Okay, in BAS, we use German words to describe the industry, and it's free floating. When a human can read it, it's good, right? In Delum, we use English, but we also use free floating. And Crunchbase actually has NC industry codes. Okay, now then I first actually have to go to every single data row of BAS and Delum and actually map it to an ANSI industry code. That takes a while. Then you have interpretation in between, right? Then currencies. Hey, we're Swiss, everything is in Swiss francs, right? Delum is whatever you put in, and Crunchbase has everything in dollars. Great. Every time I see an amount, I actually have to convert it to a currency. Which currency value am I going to take? The time that the round was done? Now? Should I calculate it every time when I update my model? It will have huge differences, right? Not so easy. Then to compare values, I always have to normalize them. So when I talk about burn rate, right, I basically have amounts in there from 0 to, I don't know, 1 million. So I could leave the amounts, but typically when you want to do some computational work, you actually want to normalize it. So you basically say, hey, doesn't matter what is in between, this is just 1, this is just 0. The same here with revenue, right? Let's say also 0, 20 million. Then 20 million is going to be 1, this is 0, and I'm going to map everything in between because I need that later to compute distances, right? The problem with that is outliers will kill me, right? So if I actually have that unicorn in my database, then everything is between 0 and 0.1, and I have my unicorn that's 1. Already meaningless, unusable, right? So I have to remove all my outliers. So even when I get data, I'm not there yet. I actually have to spend a lot of time in cleaning it. And I don't do that once. I actually want to have up-to-date data. So every new data set I get in there, I actually have to clean again, right? So owning data is actually quite expensive. Not because of the storage, but actually of the cleaning and the maintaining you have to do. So now we have clean data. Don't ask me why, but we somehow did it, right? You don't need it for every single algorithm or machine learning type, but what we need to do a lot of times is calculate distances. Because if I want to cluster I want to pretty much decide in how far is that good startup away from a bad startup, right? Or in what direction does it go? And in order to calculate distances, you basically have a number of choices. And when you have a simple two-dimensional field, like here, right, you basically have two distances or distance measures that you typically apply. The first one is the easy one. This is called the Euclidean distance, Pythagoras, the shortest path between 2 points. But it's also actually expensive to compute, because I actually have to take the square of this one, the square of this one, and then a root, right? So I have to actually make 3 quite expensive calculations. So that's why we actually take a lot of times the Manhattan distance. Why Manhattan? That's how you walk in New York. Boom, right? And you just say these two plus. This works nicely. But we have not 2 dimensions. We have many dimensions, right? And there a really fun thing happens. And this one you can forget again tomorrow, but it's actually one of the biggest problems we have when we do these computational things. When I have a 2-dimensional space and I have it full with data points, and they are all equally distributed, right? Doesn't matter where I grab, I have the same amount of data points. And now draw another box in there. My dimensions are normalized, right? So 0, 1. My distance here is 0.1, here as well, right? So when I now want to compute how many of my data points are in this border, right? It's very easy. 0 minus 0.8 squared, right? This is 0.8. So let's do the same thing in 3 dimensions. Suddenly, this becomes a 3. Hey, in 3 dimensions, more of my data points are actually at the border as in 2 dimensions. Now I have 100 dimensions. Hey, all my data points are actually at the sides of my space. That means I don't have to look in big parts of it, right? And this multidimensional behavior is extremely important to speed up algorithms, because if you have to search or compute in a very high dimensional space, this is really computational intensive, right? There are a few other behaviors in high dimensional space. The problem is our mind cannot grasp it, right? We can do 3 dimensions, then we add a 4th by adding a color, and then we're done, right? It's almost as impossible as understanding your spouse. No chance. Right? Exactly. So I already had that one. So supervised learning. I explained that is something with labels, right? These are 2 examples of that. Let's assume I have my genes, right? And I actually labeled them up front and say, okay, the people with, so I always have those 2 genes, right? And I basically have a set with 2 columns, gene 1, gene 2, and then I labeled them sick or healthy, right? Very simple. So what you then can do is run multiple algorithms to create a classifier. You can take a simple BAS classifier, you can take a support vector machine. Hey, hundreds of algorithms that you can find online, that you can use on Azure, that you can use on the Google Cloud platform. Like I said, AI is a commodity, right? and then you just have to test if it works. Well, there you come to the next problem. We talked about data, and we already said we need quite a bit of data to actually train it. Well, actually you need almost 2 times that amount of data, because not only do I need a training set, I also need a test set, and they cannot be the same, because else I would basically screw myself, right? It's basically like cheating in a test. So I need a training set that will give me this line, and then I will use a test set, and then I look how much are actually correctly classified. And that tells me something about how good the classifier is. Get to that one later. Another one, regression, right? This is only on one gene. We have another label, not just disease or healthy. We now actually have a number that says how many years a diseased person survived. Well, when you have that information, you can actually make a regression line based on the points. And when you have that, you can actually predict things, right? So, and these are very simple algorithms and models that are nowadays actually sold as AI, right? In the end, it's just statistics, right? Doesn't matter what they use, right? In the end, when you invest, it should just work, right? It should not be scientific complex. When it is, fine. If not, also fine. It should just work, right? But what does working mean? So, key point 1 was AI commodity. Key point 2, you need data. Data is a lot of work. Key point 3, confusion matrix. Very important. When you have your classifier, right, or your predictor, or even your generative AI, you can always establish such a matrix. So here we have the actual value, positive or negative, and here is the predicted one. So let's say I have 100 data points that I classify. Then I will hopefully have a number of data points where I say, yes, this is positive, and the actual value is also positive. This is true positive. I will also have a few where I say it's positive, but in the reality, it was negative. So these are your false positives. And the same with negatives. I will have classified a few as negative that actually should have been positive, and the other way around. So you should ask your startup to provide you such a matrix. When it's not on numbers, then on percentage. And the reason why is this. You have 2 measures that are absolutely key for how applicable your AI is. And that is precision, and that is recall. Precision means of all the startups that my algorithm classified as good, how many of them were really good? These 2, right? Of all the ones I predicted as positive, how many of them were actually positive? That's for our use case extremely relevant, because else I would throw my money away, right? The other one is recall. Of all the positive startups in my data set, how many of them did I classify correctly as positive? These are 2 completely different things, right? So I can have 50 winners in my data set, and I can predict 10 of them as those are winners. So when 10 of them are actually winners, my God, I should not be standing here, right? I would be on the beach for the rest of my life, right? Even when I only recall 20% of the positive startups. So amazing. But what if I would actually try to recognize cancer? Then this would be quite shitty, because 80% of my patients come out and I say, you're healthy, right? So depending on your use case, precision can be more important or recall can be more important. And that is why you need this matrix, because then you can compute both, right? And you should never be satisfied with percentages. You want to have the number of actual cases, because they tell you something about how it scales. And it also tells you something about how big their training set and their data set was. Because if I do this in percentages, fine, I take the BAS data set. Awesome. That doesn't help me. So you need to have the sample size and you need to have this matrix. If the startup is not providing it to you, walk away. Just walk away. It doesn't mean it needs to be perfect. Maybe they even can show you results, how it has improved and what they have done, change the quality of the data, additional data, a new algorithm, doesn't matter, right? But this needs to be transparent. Machine learning, it's unsupervised. So unsupervised means I don't have labels. So I have all my startups and I actually try to group them without having labeled them good or bad, right? And there are, again, a number of things that you can do there. Typical one is clustering. K-means clustering is a very known example. There are many, many other clustering examples as well. You can find them online. What K-means clustering does is it starts with one data point, right? And then it actually calculates the distance between the next data point. If that distance is shorter than a distance you have set, it takes the data point to the cluster. If the distance is bigger, it creates a new cluster. And that's how it grows to whatever number of clusters are in your data set, right? And then you can look afterwards if you can extract meaning out of those clusters. So it is really more about sense making of your data than direct applicability to a business problem, right? But it can really help to understand, for example, which features are the strongest in creating a difference in your data set, right? Because when I have 100 features and many of those features don't create a separation in your data, then I don't have to use them anymore, right? So that's how that can help. This is actually done here. PCA stands for Principal Component Analysis. What you basically do is you take all your features and then you run in pairs the clustering, and then you look where are the clusters the most separated. So this is awesome. So these features I would use for a classification algorithm. This sucks balls. It's actually one ball, right? So that's where it really helps. Reinforcement learning, the little baby. One of the best examples of this is actually the Google initiative to create machine learning, AI, whatever you want to call it, to play Go and beat the world champion, right? The special thing about it was the only thing they feeded their algorithm or the model was the rules. And then it took thousands of instances and then they let them just play against each other, right? And then every time somebody won, you looked at what was happening there. And then you try to incorporate that in the next iteration, just as how we would learn a game, right? What is there so special, especially also the way they did it, is your state, right? So basically, did you win or not, can occur far much more later after the determining move, right? So let's say you play a game of Go, you have 100 moves, and in move 32, 37, and 45, you make the absolute right moves that make sure that you win afterwards. That is then what the system should learn, right? Because a lot of the other moves are irrelevant, right? So and that's why they played millions and millions of games against each other, and then at a certain point of time, one instance that was so good that they let it play to the world champion. And then the computer won. So that's a completely different approach as what they did with chess and Kasparov, right? Because what they did with chess is they loaded every single available game, right? And they just compared the games with the board. That's totally different, right? So at that point of time, when the chess computer won, that was not intelligent. It was just a huge database of existing games. It was just Google for chess. The Go one was actually quite cool, right? What you see nowadays is that you actually have to combine one of the previous things I explained with this because you want to continue to learn. Great example of this is CAPTCHA with Google, right? You are actually working for Google every time when you select where's the bridge in this picture, right? Every time when you had those nice letters where you had to look what stands there and you think, what the fuck, nobody's writing like this, right? What they actually were doing is scanning middle-age books. They scanned every single book of the biggest libraries of the world, and you actually classified them. So, and they don't trust you. They presented the same snippet to 100 people, and the majority won. That's how you trained their OCR algorithm. That's actually how they were able to digitalize all those libraries, and you did it all for free. Just cursing, not another fucking CAPTCHA, right? So that actually works. So, deep learning. That is actually where we are today. And the most things you read in the newspaper are actually exactly that. And I try to make it as simple as possible. This is a very simple neural network. It basically has one input layer. You could imagine, for example, for a startup, every single feature is one input neuron, right? Then you have an output layer, and that is depending on the number of classes, right? In our case, it would be just 2. And then you have to decide how many hidden layers you want to have in between and how many connections you will allow. You can also leave it open, and then you let the algorithm run and run and run and run, and at a certain point of time it says, yes, I'm trained. Then you let the algorithm run on your test set. You look how well it does on the test set, and when you're happy, yay, you have your first own neural network up and running. And you can do that nowadays within a week if you have the data. Right? What you don't know is what's happening in between. You have no clue how that network decides if this is a good startup or a bad startup. You just have to trust the algorithm. And that limits the application, because in a lot of cases we need to understand things, or we want to understand things, right? So then we come back to the classification tree. What would be nicer is when you actually have that nice classification tree that says, well, if the startup is younger than 3 years and I have 2 founders with an average age about 40 and industry is automotive and, because then it's understandable, it gives you more trust, etc. But the more input parameters you have, the worse those classification trees perform. Right? So this is typically what is used nowadays, and this is actually the base for those large language models that you see. One of the first massive applications of this is actually London. Face recognition, right? Well, you're regularly in London. You have cameras everywhere, right? And they recognize faces. And they do that really, really fast, right? And they do that with any data set they can get their hands on, right? And they actually take your camera picture when you enter London, right? Even when you have a biometric one on your passport. They don't do that for traveling in London. They do that for recognizing you on the cameras in London, right? And then that data gets fed. They already have a big existing neural network, but like learning with a child, they also have reinforcement learning in place, and boom, you're part of the network and they can recognize your face. So when you then do something bad, this works really, really, really well, right? This is also what is actually running on your phone when you actually have it switched on with Apple, right? You actually have a small little neural network running there, recognizing your own face that you have trained, right? Take a picture like this, a little bit from this side, a little bit like that, boom, and it has all the data it needs to actually recognize you. And afterwards, most of us don't have any problem until you have an accident and you look funny, right? Large language models. So the new hype, and rightfully so, right? This went faster as anybody could have expected by actually an interesting combination. The development of the algorithms was done by smaller companies, and they made progress beyond expectation. And then at the same point of time, we had the large companies, the cloud hyperscalers, that saw the potential, and they basically onboarded those small companies directly onto their scaled infrastructure, right? So that's what Microsoft did with OpenAI, that's what Google did with BART, etc., right? You basically have three groupings again. Again, you can make many other groupings, but for tonight, this one isn't easy to use. Closed source, right? GPT, BART, means the model is owned by the company that created the model, right? Not the data, huh? They all stole the data. It's all your data. Then you have domain-specific LLMs, right? So for example, Bloomberg did one on their own data, and Bloomberg has a lot of data, right? So for them, it was a really powerful thing to do. You see it in the science world, actually do it on journals, doing it on gene databases. You will soon see it on DNA databases, etc. And then there we can expect really, really interesting things to happen. And then you have the open source LLMs. And then, hey, when you actually have a basement with a few powerful computers, you can download one of those models and let it train on your own thing, and then you have a model too, right? What is becoming there really interesting is for example, my client, Big Four. In theory, why would we need an army of junior consultants to create PowerPoints? I could just take every PowerPoint that we created in the last 10 years, put it in a database, run an LLM on it, right? And then I only have to ask, hey, this is a small to mid-sized company in Switzerland, automotive industry, create me a cool strategy. Flip. I get my slides, then I have a senior looking over it, done. And we're really looking into this stuff. The problem is when we don't train juniors anymore, at a certain point of time, I don't have seniors anymore, right? So not so easy. Audit, that's an interesting thing. Computers are in theory better in auditing than humans, if we have the data. So let's take an ERP, I take all the data of S4, and I'm actually going to do some revenue testing. Revenue testing means I'm actually going to cross-verify if what you reported as revenue in your ERP was actually revenue. That means I want to see that the invoice was sent out. I want to see that the payment went in, etc. Hey, I can do this all completely automatic. But now let's go to FINMA. Hey, FINMA, we just checked Credit Suisse. We think it's good. How do you know? Oh, our AI says so. That will take a while. And you will have those cases in a lot of industries, right? So from a legal point of view, we're way behind the technology developments. The other thing is we are extremely hyped about what we see, but we really make misjudgment about recall and precision. And I'll give an example of that one. It's actually called hallucination. Right? Many of these large language models, they actually think of stuff that they've never seen. Right? So it's not just that they went to a conspiracy website and they repeat bullshit they saw. No, they actually create something that they've never seen and just does not exist. This is called hallucination. Google it, you will find really cool stories. The most famous one recently was actually a lawyer in the US that got disbarred afterwards because he actually had to put a lot of work in it to create a submission for a legal case, for a lawsuit, right? He did that with ChatGTP. Hey, this is my problem, bloody, bloody, bloody. Can you write me a lawsuit submission? ChatGTP did it, right? And hey, ChatGTP and then other models already passed the bar exam, right? Easy. Hence the lawyer remark. Huh? But what he didn't think of, actually, the guy invented previous legal cases that never occurred, right? And they didn't like that so much, right? And this is actually happening more than we all think. So, yeah, playing around with ChatGTP, writing another blog post that nobody reads or understands, awesome, right? But actually using it to create a legal opinion, interesting, right? Let's assume, same Big Four, tax specialist. Right? They get paid so much money because they're always worth it, right? They only get paid when they actually create tax savings. And they get paid as soon as they make the savings. But what happens if you have legal problems afterwards, right? So currently, those specialists really make sure that they covered all grounds, because as soon as they give the tax advice, right, it's their life that pretty much hangs to it. Now we train all the AI we have on all the tax advice, all the tax laws, every single country, and then, whoop, we give you tax advice. Okay, that saves a lot of money, right? Then 1 year later, the IFRS comes by. Trust me, you'd rather have the FBI on your doorstep as the IFRS, right? So what do? I got this tax advice from an AI, right? So, and that's key point number 4 that you have to take away, right? That is, if you look at applicability of AI, you really have to look at what is actually currently allowed, right? What is done with the decision? Who relies on the decision? What are potential legal implications? Because that can really bite you in the ass afterwards, right? And that is also not really solved. So here I came to my example of Stack Overflow. I already brought the example, but here you actually see it, right? So this was 2019. This is where ChatGTP was released, and bloop, traffic. Huh? And now both have a problem. Stack Overflow has now a quality problem, and ChatGTP has a problem. The other thing that now happens is they actually already invented a tag, right, that says my website is not allowed to be crawled by a language model anymore, because they have already discovered, hey, this is a big issue. And pretty much everybody that has some information to protect now put those tags in there. So what is then the future of these models going to be? Because they can't be trained on everything anymore. So, and then if they can't be trained anymore, what is the shelf time of the ones that were trained on all the data, right? So also that is still a challenge that is not solved yet. So all in all, I'm really optimistic about where we go. At the same point of time, we're not there yet. And in the end, it's all about trust, right? How far can you rely on the outcome of an AI, and in how far is that important, right? When I offer a first level support chat, hey, I don't care if my user get a wrong answer every now and then, right? I don't care if they don't get an answer at all, right? But if I ask my doctor something, different, right? So you really have to look at the use case, really look at how important is the recall and prediction, and how important is the reliance onto this answer. So I hope I'm still in my time.
Perfect.
All right. Any questions?
No?
Good.
That's
Then
public
afterwards.
moderation.
Just okay, so now I'm going